So I'll call this point C, and that's when x equals 2. And I'll say, the derivative there, like the slope is about -1, so I'll say C prime is about -1. And then here at x equals 2.5, there is another important point, right? Here's where I'll call it D, and that's where the slope is about 0. And now I want to pick another point. It's too close to pick at, x equals 3. That's not far enough in the graph. But if I go to x equals maybe 3.5, right over here, right, you see there's a rather large slope there. And do you notice how that slope over there is the same as it was at A, relatively close anyway? So I'll say D prime is also roughly 4. Sorry, that's going to be E. So I'll say E prime is also roughly 4. Okay, so why don't we go ahead and graph that? At x equals 0, we said we have a slope of -4. So on this graph, we're going to put the values of the slope. B was at x equals 1 with a slope of 0. C was at 2 with a slope of -1. D was at x equals 2.5 with a slope of 0. And at x equals 3.5, I had a slope of 4 again. And so the difference between this curve and the one we did previously is that with this one, you see at each point, the slope is changing little by little. It's not changing abruptly. So we say the slope has a continuous change, right? And so the graph for the slope is also going to be continuous. And that's how that looks. All right. Next, we're going to go in the opposite direction. Here, we're going to be given f prime, and we have to graph the function f given the derivative. So this is y prime or f prime, and we're going to graph f. So if this is f prime, this represents the slope. And if I go and look at the slopes here, you see that in the interval from -4 to 0, the slope is -1. And in the interval from 0 to 4, the slope is +3. So in this interval from -4 to 0, the slope is constant at -1, right? Constant slope, remember, that's a linear equation. It's a linear graph. So here, to the right, I'm going to draw something with a constant slope of -1. Well, I can start anywhere on the y, as far as the y value is concerned. That's not specified to me. So let's say I start here, and then I'm just going to draw a line with the slope of -1. Okay, on the opposite side, I have a slope of 3, so that's what I'm going to draw here. So 1, 2, 3 over, 1, 2, 3 over. That's what that looks like. Okay, so let's talk about one-sided derivatives. We say a function y is differentiable on a closed interval if it has a derivative at every point on the interval. And when it comes to the endpoints, okay, A and B, right? What we have to do is we have to look at the derivative from the one side, right? And that's how we can evaluate the derivatives at the endpoints. We call those one-sided derivatives. Let's do a little bit of practice with one-sided derivatives. Take a look at this function. This is the absolute value function, right? F of x is equal to absolute value of x. This function is differentiable everywhere except at x equals 0. So let's take a look at what happens at x equals 0. If I zoom in here, throughout this interval to the left of 0, the slope is -1. And at the right of 0, the slope is positive 1. So now let's take a look at what happens at 0. If I'm at 0 and I look at the derivative to the left, it's negative 1. And if I look at the derivative to the right, it's positive 1, right? And so that abrupt change makes it not differentiable. And if you look right at 0, right, if I'm approaching 0, I have a slope of negative 1, and then immediately it changes into positive 1. And that abrupt change, again, is what makes it not differentiable. Using calculus notation, here's how we write it. We say the limit as h approaches 0 from the negative side of f of x plus h minus f of x is negative 1, so that's the left-sided limit. And the right-sided limit is positive 1. And we say because the left and right derivatives are not the same, then it's not continuous at x equals 0. As opposed to this function, f of x equals x squared. Now, in this case, this function is differentiable at x equals 0. Why? Well, look at the slopes here. Do you see how they're, changing continuously, right? And as you go in here, they just continuously change from one value to another. That's a gradual change, not an abrupt change. And if we zoom in and look at x equals 0, the slope immediately to the left is 0. It's almost horizontal. The slope immediately to the right of that point is 0. So that is differentiable at x equals 0. All right, so let's apply that to this one. We're going to use one-sided limits to show that the function below does not have a derivative at x equals 0. And we're going to use these formulas here. Okay, so I'm going to say the limit as h approaches 0 from the minus side of f of a plus h minus f of a, right, over h. Okay, so this is the one I'm using here. And look, we have f of a plus h and f of a, and a is the point where we're evaluating the limit. Here, where is the point where we are evaluating the limit? It's x equals 0, so that's my a value. So I'm going to put 0 into my a's here. Okay, so that's going to be limit as h approaches 0 from the minus side. F of a plus h, that's 0 plus h squared, minus f of a, 0 squared over h. Now, because this is the derivative immediately to the left of 0, right, you see that we're going to be using that function, right, because that's what resides to the left of 0. So this is going to be the limit as h approaches 0 from the minus side of h squared over h. Oops, h squared over h. And that's the limit as h approaches 0 from the minus side of h, so that is 0. Okay, so this is the left-sided derivative. Now, the derivative from the right it's going to be the limit as h approaches 0 from the positive side. And here we're going to look at the function to the right of 0, right? And that's this function, 2x. So again, it's going to be f of a plus h minus f of a over h. So that is the limit as h approaches 0 from the minus side. F of a plus h is 2 times 0 plus h. Minus 2 times 0, that's f of 0, f of a, over h. And that's going to be 2h over h, which cancels, so I just get 2. All right, so look at this. The limit, the derivative from the right and the derivative from the left are not the same. So we say f prime of 0 from the negative side is not equal to f prime of 0 from the positive side, Therefore, the function is not differentiable at x equals 0. And it's important to specify at x equals 0, because if you just say the function is not differentiable, it means that it's not differentiable anywhere or in other places. So you have to specify that it's at that point. Okay, thank you very much. I will see you next time.